This is the last video for your practice final exam, and I'm starting with starting with number 25 over here. It's an electron configuration problem, kind of like WebAssign 6b. So here we go with number 25, the full electron the ground state electron configuration for cobalt. So there is a periodic table on your final exam. Actually, I can show you which periodic table it is on your final exam. It is this one. No, it is this one. Yes, it is this periodic table is on your final exam. So here's cobalt, and now I'm going to write the electron configuration for it. So you got your basic S block over here, and I got 1s1, 1s2, so it's cobalt. And we go 1s2, and that's this one, the electron that fits there and right there. And here's row 2, so this is 2s2, and this is still row 2, this is 2p6, this is row 3, 3s2. We are still in row 3, this is 3p6. This is row number 4, 4s2. And this, remember, although it is row number 4, because this is the D block, we need to subtract 1 from that row number. So this is 3. D, 1, 2, 3, 4, 5, 6, 7. 3D7. Wrong button. 3D7. And that is the ground state electron configuration for Mr. Cobalt. Number 26. The ground state electron configuration for Cobalt 2+. Right, now, you may have noticed from the textbook or other readings that when you have an ion, you either add the electrons at the end. So, for example, if this were Cobalt 2-, I would add 2 electrons at the end right here. This would be +2. So this would be 3D9, okay? But if it is a positive ion, I need to remove 2 electrons from the highest shell. The shells are these numbers, the row numbers from the periodic table. 1, 2, 2, 3, 3, 4, 3. The highest shell is 4. I need to remove 2 electrons from here. I know what you're thinking. You're thinking when you add 2 electrons, so for example, if it was Cobalt 2-, why don't you add to the highest shell? Okay, the reason why you don't add to the highest shell, but instead you add just to the end here, is because this shell, it can only hold 2 electrons. The s orbital can only hold 2 electrons each. Look at that, 2 electrons, 2 electrons, 2 electrons. So there's no way to add 2 electrons here. You have to add it to the end here because the d orbital is able to take on more electrons. It can take 10. Now I know what you're thinking. You're thinking, what if the d orbital is full? That's a good question. So in the case of this guy right here, zinc, the d orbital is full. So here, let's do zinc. So zinc is just like argon. Zinc is just like argon, except it also has a 4s2, a 3d10. So if you had a zinc 2- ion, well, you would just have to add the next shell. So after 3d10, it's the 4 p's. So it's going to be 4p2, all right? What about just zinc? There, that's just zinc. What about zinc 2+? Can you figure that out? Zinc 2+? That's right. You just get rid of these 2 guys right here because they are on the highest shell, okay? That is how to do this. In nature, it makes sense that to make Cobalt 2+, you just remove the 2 electrons from the highest shell because the highest shell is supposed to be the shell of electrons that's closest to the outside. I mean, that is farthest from the nucleus. So presumably, if cobalt were to lose 2 electrons, it would lose them from the outside. Just like on a hot day, if you were to remove a piece of clothing, you would remove your jacket first. You wouldn't remove whatever you were wearing underneath that. You would remove the outer garments first. So it's the same way with atoms. Okay, number 27. What is the density of the nitrogen gas at STP? Okay, it's important for you to memorize that STP means standard temperature and pressure. That's 0 degrees Celsius, 1 atmosphere of pressure. Okay? So this question is kind of a trick because it doesn't matter what the gas is. Well, actually, no, that's not a trick. I'm sorry, never mind. So you know that density is mass over volume. So with gases, it's usually grams over liters. Okay? So to know how many grams of nitrogen gas there are in 1 liter of nitrogen gas, um, since this is STP, we could just use Avogadro's law. Avogadro's law is something that you need to memorize, and it is that 22.4 liters is the space occupied by 1 mole of any ideal gas at STP. So knowing that, see these liters here? I'm going to put them on the bottom. So I'm going to start with liters on the bottom. So I have 1 mole of nitrogen gas at STP occupies 22.4 liters. And now I have to get rid of the moles. I need to put grams up here. See, it's liters. I have liters, but I need grams on top. I want to get grams on top. So moles are on top. That's not what I want. So 1 mole of nitrogen is a certain number of grams from the periodic table. It's actually something like 28.0 grams, right? And you get the answer. 1.25. 3 significant figures, folks. 1.25 moles cancel, so it's grams per liter. Grams per liter. That's it. That's how you do 27. 28. Okay, there's a chemical reaction here. Write the equation. Right. So it's iron 3 chloride and sodium hydroxide. It's important to know about double displacement reactions. We've had that in a previous problem here, but you do not have to memorize the solubility rules. Those will be given to you on the front of the final exam. So to write this equation, this is iron 3 chloride. Now, if it's going to react with sodium hydroxide, the problem doesn't say who is solid and who is aqueous, or it doesn't say if you have solutions or what here. So it's best to just leave out the states of matter if the problem doesn't specify any of the reactants' states of matter. Sodium hydroxide, and makes iron 3 hydroxide. And sodium chloride. So there's 1 iron. There's 1 iron. That's good. There's 3 chlorides. We need 3 chlorides here. Okay. There's 1 sodium. There are 3 sodiums. Okay. There are 3 hydroxides. There are 3 hydroxides. That's good. So this is the answer for number 28. How about number 29? Using the same equation, suppose you have 25 grams. Oh, this is a limiting reactant problem. 25 grams of the first stuff and 15 grams. Oh, this is not limiting reactant. This is a percent yield. So you have 25 grams of this stuff, and you get 15 grams of this stuff, right? To figure out the percent yield, first we have to figure out how much sodium chloride can you get if you used all of these 25 grams, and if the reaction happened perfectly. The reaction never happens perfectly, but just supposing it did. So if I use all 25 grams of iron 3 chloride, and if I know the molar mass of iron 3 chloride, a certain number of grams, then I can use the fact that there's 1 of these and 3 of these. So 1 mole of iron 3 chloride will get you 3 moles of sodium chloride. And then the moles of iron 3 chloride will be cancelled, and I need to cancel the moles of sodium chloride, so 1 mole of sodium chloride is a certain number of grams. I think it's 58.444 something grams. What about the iron 3 chloride? Well, remember that you just look on the periodic table for this, so it's 1 iron, 55.845, and 3 chlorines, which is 35.45. So it's 55.845 plus 35.45 times 3. It's 162.2. 162.2 grams of iron 3 chloride and 1 mole of iron 3 chloride. The grams of iron 3 chloride cancel. The moles of sodium chloride cancel. I only have grams of sodium chloride left. And that's what they were asking for in this problem. So 25 times 3 times 58.4 divided by 162.2 is 27. But the answer is not 27. The answer is, oh, actually it is 27 because there are two significant figures here, two significant figures here. 27 grams of sodium chloride. That's the answer, folks. That's not the answer. The question is not asking for that. The question is asking for percent yield. So suppose you got 15 grams of sodium chloride. Well, you were supposed to get 27 grams of sodium chloride. So what does this mean? This means that the percent yield was what you got divided by what you were supposed to get times 100%. And that gives you 56%. You must have only two significant figures here. 56%. That's the answer. Okay? This is kind of usually the case when you make stuff in chemistry, even if you're making it in a factory. If you can get something like 66% yield, then you're doing a good job. If you can get something like 80% yield, then you deserve 50 promotions. And then if you can get like 100% yield, then you're doing something wrong because obviously no one can get 100% yield. So that's how chemistry goes when we're trying to make stuff. 30, I think I'm on number 30. Yes, I'm on number 30. Looks like we didn't see a limiting reactant problem on the final exam, which is unusual, but convenient, right? If you do not see a limiting reactant problem on the practice final exam, that means you're not going to see a limiting reactant problem on the real final exam, as far as I know. And I'm the guy who made the practice final exam. Okay, so number 30. What is this? A Hess law problem? Okay, there's no problem. I mean, there's no trouble at all. And you've done Hess law many times for your website. So here's your Hess law problem. Let's move the board over a little bit. Don't save that. Okay. So remember with Hess law, you got to add these reactions up in whatever combination is necessary to get your target reaction, which is this. Oh, looks like I'm missing a little arrow there. Sorry about that, folks. I'll see if I can fix that for you. I probably can't, but I'll try. Oh, anyways, the target reaction is CH4 plus NH3 makes HCN plus 3H2. And I'm going to make this from these guys, so I'll change colors now. All right. Now, CH4. Who has CH4? This guy has CH4, the middle guy. So I'm going to flip that equation. So I'm going to have CH4 makes C solid plus 2H2 gas. It's going to be 74.9 kilojoules per mole. It's going to be positive 74.9. Remember, it's positive because I flipped the equation. So I've got the CH4. What about the NH3? This guy has NH3. I'm going to flip that one too. So 2NH3 gas. Actually, I only need one NH3, but this equation gives me 2 NH3, so I'm going to divide this whole thing by 2. So 2 divided by 2 is just going to be NH3 gas. And this is 1 divided by 2 and N2. 1 divided by 2 N2 gas. This is 3 divided by 2 H2. 3 divided by 2 H2 gas. And this guy is also divided by 2, so but it's also flipped. So positive 91.8 divided by 2 is positive 45.9. Okay, so I've got an H3. Now I need to make sure I have HCN in the products. Okay, HCN is right here. I only need one HCN, but there are two here, so I'm going to divide this whole thing by 2. I'm not going to flip it though, because this HCN is after the arrow, and my HCN is also after the arrow, although the arrow didn't show up here, sorry. So 1/2 of those. 2 divided by 2 is 1, plus 1/2 of a nitrogen makes HCN. Right, and now I divided everything by 2. I did not flip, so this is going to be positive 135.2. 135.2 kilojoules per mole. All right, so let me verify that these all add up to the green equation. I see that I have N2 in the products over here, and I have N2 in the reactants over here. 1/2 of N2, 1/2 of N2. Here I have 1/2 of an H2 over here. We have 3/2 of an H2, so 3/2 minus 1/2 is just 1. This is 1 H2 gas. Here I have a carbon in the products, and here I have carbon in the reactants. So that gets canceled. So the sum, final sum, is CH4 and NH3. Oh, look. Oh, I'm sorry. This is crossed out. This 1/2 of H2, this is crossed out. All right, so makes 2 H2s. Oh, no. It looks like it makes 3 H2s because there's 2 here and there's 1 here. So 3 H2s plus an HCN. And that's it. The red equation matches the green equation, so that means my acrobatics here in purple were correct, and I can just add up these numbers now to get the delta H of this reaction. The circle indicates that this is done in standard conditions, meaning 1 atmosphere of pressure. Standard conditions. I believe that it would also indicate the temperature, but I'm not sure of that. But that's not important. What's important is that we add these up. Okay, so it's 256 kilojoules per mole. Interestingly, this is positive. That's unusual. That means it requires energy. To do this reaction, you have to give it energy. You have to give this chemical reaction energy the whole time. It's never going to go by itself. It's always going to be absorbing heat or some form of energy. Probably heat. In other words, when you do this reaction, the temperature is going to drop a little bit. That's a little unusual. I see. Yes, this is not unusual because you have 2 moles of stuff total here. There's 1 mole of CH4, 1 mole of NH3. You have 4 moles of stuff total here. There are 3 moles of this and 1 mole of that. So when you start with 2 moles and you end with 4 moles, obviously you've broken a bunch of bonds and you have not reformed a bunch of bonds. Forming bonds releases energy. Breaking bonds requires energy. So the net activity here is the breaking of bonds. So that's why it requires energy. So anyway, that's the answer for the last problem. I'm sorry, terribly sorry that this is so late. I just had a hard time getting it all together. But good luck on your final exam. I will post an announcement with the various items that I think you should memorize before your final exam. Please reserve time with your proctor for your final exam in the next half hour because it is necessary to do that 24 hours in advance. Thank you.